Section 13.8 is on extrema of functions of two variables. Our objectives are to find absolute and relative extrema of functions of two variables and to use the second partials test to find the relative extrema of functions of two variables. These pictures show examples of absolute and relative extrema. We say this is a surface. You can see where there is a maximum highest point on the surface as well as these minimum points on the surface. We say that these are the absolute extrema for this closed bounded region R, the very lowest of the entire surface. We have the minimums, absolute minimums, and the highest point on the surface in that region is our absolute maximum. Now here we have on the right side examples of relative extrema. We have quite a few high points. Over here, it's not the highest point for the entire surface, but it is a high point. We call it a relative maximum. And as well as we have some low points here, a relative minimum. To locate relative extrema of f, you can investigate the points at which the gradient of f is 0 or does not exist. What we're going to do is find critical points. If f is a function defined on an open region, then we can say that x0, y0 is a critical point if one of the following is true. Either number one, the partial derivative with respect to x is equal to 0 and the partial derivative with respect to y is equal to 0. They must both be 0, or option 2, either the partial with respect to x or y does not exist. Those are going to be our critical points. The relative extrema occur only at those critical points. Now here we have a surface, and you can tell by looking at the surface that there's a relative maxima. Right there, the gradient is equal to 0. That means the partial with respect to x is equal to 0, and with respect to y, it's equal to 0 at the same time. Here we have a surface on the right that has a relative minimum. The gradient at that point is also 0. That means the partial derivative with respect to x is equal to 0 and with respect to y is equal to 0. In this example, we're going to be finding the relative extrema. Determine the relative extrema of this function f of xy equals 2x squared plus y squared plus 8x minus 6y plus 20. We can find the gradient by finding those partial derivatives, or find those critical points by finding the partial derivative with respect to x, find out where that is equal to 0, and then take the partial derivative with respect to y, find out where that is also equal to 0. Okay, if you take the partial derivative with respect to x, you treat x as a variable and everything else as a constant. That derivative is 4x plus 8. And the partial derivative with respect to y is equal to 2y minus 6. Now we're going to set them both equal to 0. 4x plus 8 equals 0. Solve that by subtracting 8 and dividing by 2. Dividing by 4. X is equal to negative 2. And set this equal to 0. Add 6 and divide by 2 to get 3. So when x is negative 2 and y is 3, that's our critical point. So if you set them both equal to 0, you get the critical point negative 2, 3. Now this is going to be a possible relative extrema, could be a relative minimum or relative maximum. To determine what type of, which one it is, either a maximum or minimum, you can rewrite the original function by completing the square. And you'll see that this is an elliptic paraboloid. Okay, so in this case, that is your relative minimum. I'm sorry, it's not your... All right, sorry, I apologize for that. This is an elliptic paraboloid. It is a parabola that opens up in both the x and the y directions, so it would make sense if it's a paraboloid that opens up, that critical point where the gradient is equal to 0 is your relative minimum. Okay, and another way you can look at it is if you can determine the graph of the function and look right there at the critical point, we could tell that it is a relative minimum. Now the way we get the actual point in space, if you're given you found the x and the y as your critical point, -2, 3. If you plug that into the original equation for the surface and evaluate, you get the 3 as your z value. So that's your point in space. That is your relative minimum. Now we are going to be using the second partials test to determine whether we have extrema, maxima, or minima, or even saddle points. The critical points of a function of two variables do not always yield a relative maxima or minima. Some critical points yield saddle points, which are neither relative maxima nor minima. And this is called a saddle point because it looks like a saddle. Looking at it in one direction, you see the parabola that opens up, and looking at it from another direction, you see the parabola that opens down. Kind of looks like the shape of a Pringles potato chip. We call that a saddle point. Now at the saddle point in this case, the partial derivative with respect to x and y are both 0 at the same time. Now this is our second partials test, which gives us a way to determine if we have relative max, a relative min, or a saddle point without having to refer to a graph. In this case, we're looking at f, which is a function of two variables, and we're finding the critical points where the partial with respect to x and y are both 0 at the same time. To test for a relative extrema, you want to consider the quantity d equals, right here, fxx, that's your second partial derivative with respect to x evaluated at the critical point. The second partial is with respect to y minus that mixed partial with respect to x and then y squared. This is what we call determinant. You're going to find the critical points by setting the first partial is equal to 0. Then you're going to find the second partials and the mixed partials, evaluate those, and evaluate this quantity to find a value for d. If d is greater than 0 and the second partial with respect to x is greater than 0, then we could say f has a relative minimum at AB, at that critical point. If the d is greater than 0 and the second partial with respect to x is less than 0, then we say f has a relative maxima. If d is less than 0, then we say that point is a saddle point. Now, if for some reason when you evaluate it, you get d equals 0, the test is inconclusive. That means you cannot determine if there's a relative max or min simply by plugging it in. You would have to use other approaches to finding if indeed it's a relative max or min, using technology to graph it or knowing basics about the equation. Now this is similar when you worked in Calc 1, Calc 2, you did the second derivative test for concavity. Well, this in a way relates where when you take the first derivative equals 0, that's when you have that possible relative max or min, and that second derivative, if it's concave up or concave down, you can determine if it's a relative max or min. So this second partials test incorporates that into this to determine, to test for the relative extrema. In this example, we're using the second partials test to find the relative extrema of f of xy equals negative x cubed plus 4xy minus 2y squared plus 1. To begin, we find the critical points of f. The critical points are where the partial with respect to x equals 0 and the partial with respect to y equals 0. When you take the partial with respect to x, treat x as a variable and y as a constant to get negative 3x squared plus 4y. You take the partial derivative with respect to y, you treat y as a variable and x as a constant to get 4x minus 4y. We say that we want to find out where these are both equal to 0. To locate these points, we're going to set them both equal to 0 to get these equations. And then by using substitution, well, the first equation We're going to leave it as it is, but the second equation, 4x minus 4y equals 0, by adding 4y to both sides, you get 4x equals 4y, and then by dividing by 4, you get x equals y. So from the second equation, we get the x equals y. Now we're going to plug that back into the first equation to get the equation negative 3x squared plus 3x equals 0. Now that's a quadratic equation. You can solve it by factoring or using the quadratic formula, and you're going to end up with two solutions. You can factor out an x to get x equals 0, and then when you set the other factor equal to 0, the negative 3x plus 4 equal to 0, and solve that, you get x equals 4/3. And then by plugging that back into x equals y, you get the critical points. So this one has two critical points, one at 0, 0, and one at 4/3, 4/3. To use a second partials test, you want to find the higher order partial derivatives, and you're going to plug in those critical. So we actually have two critical points. We're going to plug them both into that second partials test. We need to take the higher order partial derivatives, so the second partial with respect to x is negative 6x, the second partial with respect to y is negative 4, and the mixed partial is 4. So when you're testing the first critical point, 0, 0, plugging that in, 0 for x, 0 for y, and you evaluate that d, that determinant, the partial with respect to x is 0, the higher order partial with respect to x and y, that's going to be 0 times negative 4, so that's 0. And then that mixed partial is 4. You square it, it's going to be 0 minus 16. And that's a negative number, it's less than 0. So by the second partials test, you can conclude that the 0, 0 is a saddle point. To get the 1, you're going to plug 0 back into x and y, back into the original equation to get 1. Okay, now you also need to evaluate the d for the other critical point, 4/3, 4/3. So you take the higher order partial derivatives and evaluate them at 4/3. The second partial with respect to x evaluated at 4/3 is negative 8. The second partial with respect to y evaluated at 4/3 is negative 4. And the mixed partial is 4 squared, you get 16. So we're going to multiply negative 8 times negative 4 and subtract 16, and that gives us a positive number. All right, since the d is positive, it's greater than 0, and the second derivative with respect to x is negative. Think about this. It's concavity is negative, so it's concave down. We can say that's greater than 0. We can say that it is a relative maximum at the point 4/3, 4/3. So this picture is showing the surface. We have the saddle point at 0, 0, and the relative maxima at 4/3, 4/3.